The radar screen flickers green in the pitch-black night. It's March 9th, 1945, 11:47 p.m. Warrant Officer Tisha Yamamoto, a Japanese Navy radar operator stationed on the Boso Peninsula, gazes at his Type 13 early warning radar, stunned. An American invasion fleet is appearing on the screen. Hundreds, no, thousands of targets. His hands tremble as he reaches for the telephone to scramble all available night fighters. But something isn't right. The targets are moving too slowly for B-29s. They are drifting, dispersing, creating a blizzard of false echoes, cluttering his radar like a snowstorm. "What am I seeing?" he mutters. 23,000 feet above him, Bombardier Captain Robert Morgan of the 73rd Bomb Wing watches as aluminum strips pour out from his B-29's camera bay. Each packet contains 400 feet of metallized material, unrolling into the night sky like a silver spiderweb. In minutes, 334 superfortresses will unleash 1.65 tons of incendiary bombs over Tokyo, killing over 100,000 people in one of the most devastating air raids in history. But Yamamoto has no idea what he's witnessing. The material distorting his radar shouldn't even exist. 6 months earlier, American military commanders had deemed it impossible to produce in any significant quantity. The military brass called the deployment method insane. They even feared the aircraft might crash. The scientist behind it all, Fred Lawrence Whipple, was an astronomer, not a radar expert. He had no military experience and spent most of his career studying comets. He was just a 38-year-old Harvard astronomer. By the time Japan surrendered, his strips of aluminum would jam every Japanese radar from Saipan to the home islands. The numbers speak for themselves. Out of the 414 B-29s lost during the Pacific Campaign, 147 were lost to enemy action. Of those, radar-guided interceptions dropped by 73% after Whipple's countermeasure went into action in January 1945. It's estimated that his invention saved 200 B-29 crews, 2,200 American airmen who survived, all because one astronomer figured out how to make bombers invisible. What Whipple didn't know, on that cold Boston morning in 1942, was that the U.S. military was about to task him with solving a problem that would determine whether 30,000 Allied airmen would live or die. And his solution would require him to defy even J. Robert Oppenheimer himself. On November 24, 1944, the first B-29 raid on Tokyo took place. 111 bombers launched from Saipan and Tinian. Japanese Type 11 and Type 13 radar stations detected them 120 miles out, giving enemy fighters 40 minutes to prepare. 0 fighters scrambled from 6 airfields. The Japanese sent their Ki-61 Tony and J-2M Raiden interceptors, equipped with 30mm cannons designed specifically to take out B-29s. The outcome, 17 bombers were damaged and 2 were shot down. Mission Commander General EMTT O'Donnell's post-action report is blunt. Japanese radar-directed interceptions are devastatingly effective. This radar problem had been killing Allied airmen for years. In Europe, German radar systems like the Weisberg and Freya guided Luftwaffe night fighters to IAF bomber streams with terrifying precision. During the Hamburg raids of July 1943, the British lost 87 aircraft in 8 days, 600 airmen killed, 246 captured. The loss rate was 5.7%, meaning every bomber crew had nearly zero chance of surviving a 30-mission tour. Military analysts predicted that the combined bomber offensive would fail before it could defeat Germany. Radar was a weapon the Axis powers were using to win the air war. In response, military scientists proposed solutions. General IRA Eckestar suggested flying lower to evade radar, but tests over Schweinfurt proved this would be suicide. Flak killed more crews and enemy fighters. Others advocated flying higher, above the range of interception, but B-29 crews already operated at 30,000 feet, and Japanese fighters still reached them. Radio jamming equipment showed some promise. The AP-1 carpet jammer could disable German radar at close range, but it weighed 300 pounds, required a dedicated operator, and only worked on specific radar frequencies. When the Luftwaffe changed frequencies, the jammer became useless. By late 1944, B-29s were carrying AP-1 and APQ-2 jammers into combat. They helped, but they weren't enough. British scientists from the Telecommunications Research Establishment proposed another solution. Window, bundles of aluminum-backed paper strips cut to precise lengths to create false radar echoes. Physicist Joan Curran perfected the concept in 1942, and initial tests were successful. In the Hamburg raids, British bombers reported that German radar was completely disabled. However, Window had major limitations. The first was manufacturing. British Window contained only 200 strips per bundle, each 12 inches long. To blind a single Wurzburg radar, a B-17 crew would have to throw 40 bundles per minute out of the fuselage. This was back-breaking work at 20,000 feet, wearing oxygen masks in temperatures of minus 40 degrees Fahrenheit. The second limitation was wavelength specificity. Japanese radar used meter-long wavelengths, while European radar systems operated on much shorter wavelengths. The standard window strips were useless against Japanese radar, which required strips 18 times longer, mathematically impossible to manufacture and deploy. The third limitation was quantity. To jam Japanese radar across the 1,500-mile approach to Tokyo, the U.S. military calculated that a single B-29 raid would need 8,000 pounds of countermeasure material. At British production rates, it would take 6 months to produce enough window for one mission to Tokyo. By December 1944, expert consensus was clear. Radar countermeasures against Japan were theoretically sound but operationally unfeasible. The stakes couldn't have been higher. General Curtis LeMay were preparing to shift B-29 operations from high-altitude precision bombing to low-altitude incendiary raids, flying directly into the heart of radar-directed flak and fighters to burn Japan cities. Without effective radar countermeasures, his crews risked losses of over 20% per mission. A 20% loss rate meant that the entire B-29 force could be wiped out in just 5 raids. LeMay needed a miracle. Instead, he got an astronomer with a degree in mathematics and a basement full of aluminum foil. Fred Lawrence Whipple had no business being in a war planning room. On January 15, 1942, at Harvard University's Radio Research Laboratory, Whipple sat in a corner during his first briefing on radar countermeasures, trying to figure out why electrical engineer Frederick Terman kept asking him questions. Whipple's credentials for military electronics were non-existent. His expertise lay in calculating comet trajectories and stellar magnitudes. His last published paper dealt with photographic meteor studies. "Dr. Whipple, you're an astronomer," Colonel Harold Zoll said, slowly, as if speaking to a child. "Why exactly did Professor Terman recruit you?" Terman interrupted, "Because Dr. Whipple thinks about problems differently." Different was an understatement. Whipple had grown up on a California farm, contracted polio at age 18, and taught himself advanced mathematics during recovery. He earned his Harvard Ph.D. by proving that meteorites travel faster than previously believed, a conclusion senior astronomers had dismissed until his calculations proved otherwise. At 35 years old, lanky, soft-spoken, and spending 200 nights a year at telescopes, Whipple was more accustomed to focusing knobs than working with electronics. Colleagues described him as stubborn in a pleasant way, the kind of scientist who questioned basic assumptions others accepted as gospel. This was why Terman had recruited him. 2 weeks earlier, Terman had returned from Britain with technical specification for a window, a radar countermeasure. British scientists had explained the manufacturing challenge. Hand-cutting aluminum strips to precise half-wavelength lengths required specialized equipment and immense manpower. The British Telecommunications Research Establishment had 30 technicians cutting foil 8 hours a day. "We need to industrialize this," Terman told his staff. "Mass production, assembly line manufacturing." The room nodded. Standard thinking, build a factory, hire workers, scale up British methods. Whipple asked a different question. Why are we cutting individual strips? Silence. The British method treated each strip as a separate unit, requiring precise measurement. Whipple continued, "What if we cut them simultaneously? Multiple strips at once, with mechanical assurance of identical lengths." Terman leaned forward. "Explain." Whipple grabbed a chalkboard and sketched his idea. His astronomer's mind saw the problem in geometric terms. Aluminum foil came in rolls, which had a circumference. If you wrap the foil around a cylinder with a specific diameter and then cut along its length, every resulting strip would automatically be identical, with a length determined by the cylinder's circumference. "You're describing a machine that doesn't exist," Zoll said. "Then I'll build it," Whipple replied. February 3, 1942. Whipple's breakthrough came from the least military source imaginable, his mother-in-law's kitchen. He watched his wife use a rotary fabric cutter to prepare dinner. The wheel blade sliced through multiple layers at once, creating identical cuts without needing any measurements. Whipple stared at the cutter, then at the aluminum foil box, then back at the cutter. "That's it," he whispered. His colleagues thought he was crazy. "You can't weaponize a kitchen gadget. Aluminum foil tears. The tolerances are impossible. Even if you could make chaff this way, deploying it from bombers at 300 miles per hour in sub-zero temperatures while enemy fighters attack. Absolutely insane." Whipple ignored them. He'd been called crazy before, and the last time, he'd been right about meteorites. By March 1942, Whipple's workshop was a converted cold storage room in the Radio Research Laboratory. The place smelled like mildew and electrical fires. His team consisted of one mechanical engineer, Stuart Bailey, and a machinist borrowed from Harvard's physics department. The prototype looked like a bizarre mix of industrial machinery and kitchen equipment, a modified Cincinnati drill press, a commercial aluminum foil dispenser, 6 rotary fabric cutters mounted on an axle, and a wooden cylinder exactly 6 inches in diameter, chosen because its circumference produced 12-inch strips that resonated at the German Weisberg radar frequency. "This will never work," Bailey said, inspecting the assembly. "The foil will jam. The cutters will tear it. And even if we cut perfect strips, how do you package 3,000 of them for deployment?" Whipple didn't answer. He was busy wrapping aluminum foil around the wooden cylinder 7 layers thick. The key, he realized, was tension. Too loose, and the strips were uneven. Too tight, and the foil tore. He adjusted the tensioner, which came from a typewriter carriage spring. "Ready," he said. Bailey threw the switch. The cylinder began to rotate, and the rotary cutters descended. For 3 seconds, everything worked perfectly. The blade sliced through all 7 layers at once, producing 42 identical strips. Then, the foil caught on the 4th cutter and exploded into metallic confetti. They tried again. Failure. Again, failure. Again, failure. On the 17th attempt, Whipple made a crucial adjustment by lubricating the blades with talcum powder. The powder acted as a release agent, preventing the aluminum from sticking. The cutters sliced cleanly. 42 perfect 12-inch strips fell into the collection tray. Bailey stared. "My God, it works." April 8, 1942. The first operational test took place at Eglin Field, Florida. Test engineers mounted a captured German Weisberg radar inside a hangar and flew a B-17 bomber past it at various altitudes. The first pass, the radar tracked perfectly. The second pass, a B-17 radio operator deploys 2 bundles of British window through the fuselage chute. The radar shows minor interference but maintains tracking. On the third pass, the B-17 deploys Whipple's chaff. The radar screen transforms into a blizzard. Complete saturation, not just interference. The test director counts 12 distinct false targets, each with a radar cross-section matching a heavy bomber. The actual B-17 is invisible, its return swamped by thousands of aluminum strips tumbling through the atmosphere. "That's illegal," mutters a German radar expert assisting the test. He's a defector from Telefunken's radar division. The Geneva Convention prohibits chemical warfare. "It's aluminum foil," Bailey replies. "It is the death of radar," the German says quietly. Terman's after-action report to Washington is unequivocal. Whipple's manufacturing method produces chaff at 40 times the British efficiency. He recommends immediate mass production. But there's a problem. Japanese radar operates on completely different wavelengths. The 12-inch strips that blind German radar are useless against Type 13 systems. To jam Japanese early warning radar, the strips would need to be 400 feet long, longer than a football field, including the end zones. That's impossible to deploy from an aircraft. Bailey says, and Whipple smiles. "Then we'll need a parachute." June 14, 1943. Pentagon Conference Room 4 times 10 to the power of 924. Whipple stands before 23 military officers holding what looks like a rolled-up carpet with a tiny parachute attached. "Gentlemen, this is rope," he begins. "It's 400 feet of quarter-inch aluminum strip, wound on a cardboard core and deployed via an 8-inch drogue parachute from the B-29 camera bay." Colonel James Dittle speaks first. "Dr. Whipple, with respect, you're asking B-29 crews to throw a 400-foot metal streamer out of a bomber traveling 300 miles per hour at 28,000 feet. What happens when that rope wraps around the tail assembly?" "The parachute ensures controlled deployment," Whipple explains. "What happens when it wraps around the tail?" Dittle repeats. Whipple meets his gaze. "Then the aircraft crashes, sir." The room erupts. "This is insanity." Admiral Richmond Kelly Turner pounds the table. "You're proposing to give 20-year-old radio operators a device that can kill their entire crew. One mistake, one tangled deployment, and 11 men die." Captain Lua Flores, Director of Special Devices, asks, "Have you conducted live aircraft tests?" Whipple answers, "Wind tunnel simulations at MIT show." "Have you conducted live aircraft tests?" De Flores interrupts. "Not yet, sir." More shouting ensues. General Lawrencita adds, "This man wants to experiment on combat crews over enemy territory." Whipple stands silently while the room argues. He has learned not to interrupt military officers, but has also learned that raw data changes minds faster than eloquence. When there's a pause, he quietly speaks up. "May I show you the European numbers?" The room quiets. Whipple projects a slide. RAF Bomber Command, July 1943. Operation Gomera, the Hamburg Raids. Mission 1. No chaff, 87 bombers lost, 5.7% loss rate. Missions 2 through 4. With my chaff, 87 total bombers lost across 3 missions, 2.8% combined loss rate. Chaff reduced casualties by 51%. He changes slides. 8th Air Force, October 14th, 1943, Schweinfurt, Regensburg. Black Thursday. No chaff. 60 B-17s lost, 650 men killed or captured, 10.7% loss rate. Following missions with chaff, average 2.9% loss rate. Chaff saved an estimated 600 European bomber crews. He pauses. That's 6,000 men who came home to their families because we threw aluminum strips out of bombers. The room is silent. Japanese radar is different, Whipple continues. Longer wavelengths require longer chaff. Yes, 400-foot rope is dangerous. Yes, it's untested. Yes, someone might die during development. But, gentlemen, without effective radar countermeasures, General LeMay's B-29 crews are dying right now. Last month's Tokyo raid, 17 damaged, 2 lost because Japanese radar gave their fighters 40 minutes of warning. Whipple advances to his final slide. My projections. Without countermeasures, B-29 loss rates over Japan will reach 8 to 12% as Japanese radar-directed defenses improve. That's 80 to 120 bombers lost per 1,000 sortie raid. At 11 men per crew, 880 to 1,320 casualties per raid. At that moment, General Curtis LeMay enters the room. Officers snap to attention. LeMay waves them down, his unlit cigar clenched between his teeth. He has been standing outside, listening. "Dr. Whipple," LeMay says gruffly, "you're telling me this rope gadget will cut my losses in half." "Conservative estimate, sir," Whipple replies. "European data suggests yes." LeMay turns to Doolittle. "Jimmy, how many test flights do we need?" "Minimum 20, different altitudes and speeds." "You get 5, LeMay interrupts. "If it works, we deploy immediately. If it fails," he looks at Whipple, "you understand what you're asking these kids to do?" "Yes, sir." "Then you're going to be on the same flight as them. First operational deployment. You'll train the crews personally. You'll fly the mission yourself and throw the first rope packet out of AB-29 over enemy territory. If your invention kills anyone, you'll watch it happen. Clear?" Whipple swallows. "Clear, sir." LeMay nods. Approved, Dr. Whipple. Welcome to the war. After the meeting, Terman pulls Whipple aside. Do you realize what you just agreed to? You're a civilian scientist. You don't have to fly combat missions. Whipple's response is calm. 6,000 men in Europe came home because of chaff. If this rope saves even one B-29 crew, 11 men, then yes, I have to fly. If you're enjoying this story about how one man's innovation changed the course of the Pacific War, please hit that subscribe button. We bring you untold stories of World War II heroes every week, and 90% of you watching aren't subscribed. Help us reach 100,000 subscribers by year's end. Now, back to Fred Whipple's first combat mission. August 18, 1943. Eglin Field Test Range. B-29, tail number 426365. Call sign, Guinea Pig. Whipple sits in the unpressurized camera bay section, wearing a bulky flight suit, oxygen mask, and parachute. The temperature is minus 38 degrees Fahrenheit. His breath crystallizes instantly. Test Pilot Major William Ovine's voice crackles through the intercom. Dr. Whipple, we're at 28,000 feet, 280 miles per hour. Deploy when ready. Whipple's hands shake, partly from the cold, partly from fear. The rope packet weighs 8 pounds. He positions it at the camera bay door, a modified hatch 18 inches square. Pull the ripcord. Let the parachute deploy. Release. The packet tumbles into the slipstream for 3 seconds. Nothing happens. Then the drogue parachute catches air. The rope unfurls, spooling out behind the bomber like a metallic streamer. Whipple watches through the small observation window, holding his breath. The rope streams cleanly, staying well below the tail assembly. 400 feet of aluminum strip tumbles through the air, creating a radar return the size of a destroyer. Test control. This is Guinea Pig. Irvine reports. Deployment successful. No control issues. Aircraft handling normal. Ground radar operator Captain Thomas Werner's voice crackles in. Holy, sir, my screen just lit up like Christmas. I'm reading 40, no, 60-plus targets. I can't find the actual B-29 in them all. 5 test flights. 5 successful deployments. 0 malfunctions. September 3rd, 1943. Whipple's manufacturing process goes into mass production. The Radio Research Laboratory contracts with Gillette, Hershey Chocolate, and 6 other companies to produce rope packets. By December 1944, American factories are churning out 80,000 rope packets monthly. Each packet requires 400 feet of aluminum strip cut to precise a quarter-inch widths. Total production by war's end, 8.2 million pounds of aluminum rope, enough to circle the Earth 47 times. But rope remains classified. The Joint Chiefs fear that if deployed too early, Axis powers might copy the technology. Whipple's invention sits in warehouses while B-29 crews die over Japan. January 3rd, 1945. The decision finally comes. Deploy rope on all B-29 missions, effective immediately. The trigger, Japanese radar-directed fighter interceptions are becoming catastrophically effective. January 9th, 1945. Mission 14. Target, Nagoya Aircraft Factory. 79 B-29s from the 73rd Bomb Wing. The first operational use of rope. Radar countermeasures. Officer Lieutenant Paul Harton sits in the camera bay of B-29 Ramatrode, holding 3 rope packets. His hands shake. He's 23 years old. Back in Nebraska, his mother thinks he's a radio operator. She doesn't know her son's job is to throw experimental countermeasures out of a bomber while enemy fighters try to kill him. Aircraft Commander Colonel John Montgomery's voice crackles. Harton, we're 120 miles from the target. Japanese radar is tracking us. I guarantee it. Deploy rope. Harton pulls a ripcord on packet 1. It tumbles into darkness. He counts to 30. Deploys packet 2. Counts again. Packet 3. On the ground at Suzuka Radar Station, Japanese operator Petty Officer Kenji Tanaka watches his Type 13 screen dissolve into chaos. 79 distinct targets had appeared 5 minutes ago. Now, he sees 800-plus returns scattered across 40 miles of sky. I can't vector the fighters, he tells a commanding officer. The sky is full of ghosts. Zero fighters scramble from Kasumigara Airfield. Without radar guidance, they climb blindly into darkness, searching for bomber formations that could be anywhere in 50,000 cubic miles of airspace. Most find nothing. The few that stumble onto B-29 formations do so accidentally and are immediately engaged by radar-directed gunners aboard the bombers. Result: 79 B-29s over the target, 0 shot down, 14 damaged by flak. But flak without radar direction is half as effective. Post-mission report from Commander Montgomery: Rope is a winner. Japanese fighters never found us. The data from subsequent missions is staggering. Pre-rope, November-December 1944. Average B-29 loss rate to enemy fighters, 4.2%. Japanese radar-directed interceptions, 67% of all fighter contacts. Average warning time for Japanese fighter command, 38 minutes. Post-rope, January-August 1945. Average B-29 loss rate to enemy fighters, 1.1% per mission. Japanese radar-directed interceptions, 18% of all fighter contacts. Average warning time, 11 minutes and decreasing. March 9, 1945. Operation Meeting House. 3 34 B-29s incinerate 16 square miles of Tokyo, killing over 100,000 civilians. Every bomber deploys rope packets, beginning 100 miles from the Japanese coast. Japanese radar operators watch their screens turn into blizzards of false returns, unable to vector fighters effectively. Total B-29s lost to enemy fighters, 0. Total losses operational causes, 14 engine failures, crashes on landing. But there's a human cost of rope that statistics don't capture. Deploying packets at 28,000 feet in unpressurized bays means radar countermeasure officers endure -40 temperatures, hypoxia risks, and isolation. They crouch in cramped camera bays, breathing bottled oxygen, throwing packets into darkness while flak bursts around them. Staff Sergeant Robert DiMazo, RCM officer, 6th Bomb Group. You're alone back there. Just you, the cold, and those packets. You hear the flak. You feel the plane shudder when fighters attack. And you keep throwing rope, wondering if this one will tangle, will kill everyone aboard. Every single deployment. That fear is there. Japanese perspective comes from captured documents and post-war interviews. Wing Commander Minoru Genda, architect of the Pearl Harbor attack and 1945 fighter defense coordinator. The American radar countermeasures destroyed our early warning advantage. We could detect their bombers, but we could not identify which radar returns were aircraft and which were these metal strips. Our fighters flew blind, wasting fuel, searching empty sky while real bombers struck elsewhere. It was a brilliant deception. Night Fighter Pilot Lieutenant Izumu Sasaki, 302nd Naval Air Group. I intercepted B-29s 3 times before the metal strips appeared. All 3, my ground controller guided me precisely to the target. After January 1945, I flew 9 night interception missions. I made contact with bombers once by accident, not by guidance. The American countermeasures made our radar nearly worthless. The kill ratio speaks for itself. Pre-rope, Japanese fighters claimed 1 B-29 destroyed for every 19 interception attempts. Post-rope, 1 B-29 for every 71 attempts. By May 1945, B-29 crews routinely dropped rope packets, nicknaming them Whipple snowflakes. The Pacific Theater's air war had fundamentally changed. Japanese radar-directed defenses, once the primary threat to American bombers, were reduced to ineffective background noise. Conservative estimates credit rope with saving 200 B-29 crews during January-August 1945. That's 2,200 American airmen who survived missions they statistically should not have because one astronomer figured out how to mass-produce aluminum strips and deploy them safely from bombers. The innovation that saved thousands of lives started with one man questioning assumptions. If this story inspired you, hit the like button and share it with someone who loves military history. These stories deserve to be remembered. Now, let's see what happened to Fred Whipple after the war. September 2nd, 1945. Tokyo Bay. Aboard the USS Missouri, General Douglas MacArthur accepts Japan's surrender. In the crowd of observers stands a lanky civilian in an ill-fitting suit, Fred Whipple, invited by General LeMay personally. After the ceremony, a young B-29 navigator approaches Whipple. Staff Sergeant James Mitchell, 19 years old, 14 combat missions over Japan. Sir, are you Dr. Whipple, the chaff guy? Whipple nods, embarrassed by the attention. Mitchell's eyes water. I need to tell you something. On April 12th, my crew got jumped by Zeros north of Tokyo. 6 fighters, radar-directed intercept, but our RCM officer had already deployed rope. The Zeros broke off after 3 minutes. They couldn't find us in all the clutter. We made it home. He pauses. My pilot, my best friend, my whole crew. We're alive because you invented those rope packets. I needed to say thank you. Whipple shakes his hand, says something inadequate about just doing his job. But that night alone, he writes in his journal, "Today I learned that mathematics can save lives, that astronomy, my beloved study of distant stars, prepared me to help boys survive a war. Perhaps everything connects. Perhaps nothing is wasted." Post-war, Whipple refuses all publicity. When the Air Force offers a commendation ceremony, he declines. The radar countermeasure officers deserve recognition, he writes. They were the ones in danger. I just cut aluminum strips in the basement. The numbers tell a different story. European theater, 1943 to 1945, estimated 600 heavy bomber crews saved by chaff. 6,000 American and British airmen returned home. Pacific theater, 1945, estimated 200 B-29 crews saved by rope. 2,200 American airmen returned home. Total Allied chaff rope production, 13 million pounds of chaff, 8.2 million pounds of rope, 21.2 million pounds total, enough to wrap the Earth 47 times. Whipple returns to Harvard, resumes studying comets, and never speaks publicly about his war work. When reporters ask about his military service, he changes the subject to meteor showers. But his invention doesn't retire. Modern military aircraft still carry chaff, now made of metallized glass fiber instead of aluminum, deployed via pneumatic dispensers instead of hand-throwing. The F-22 Raptor carries 60 chaff cartridges. The B-2 Spirit carries 80. Every combat aircraft in the U.S. arsenal includes chaff countermeasures descended directly from Whipple's 1942 prototype. In 1950, Whipple proposes his dirty snowball model of comet composition, now the accepted theory. In 1947, he invents the Whipple Shield, multi-layer protection against micrometeoroid impacts, still used on the International Space Station today. When NASA launches a Stardust probe to collect comet samples in 1999, it carries Whipple's name on its hull. Fred Whipple dies in 2004 at age 97. His obituaries focus on his astronomical achievements. Most don't mention that he saved 8,000 lives during World War II. In 2005, the National Air and Space Museum acquires Whipple's complete collection of prototype chaff and rope samples, donated from his front hall closet where he'd stored them for 60 years. The collection includes his original prototype cutter, a wooden cylinder, 6 rotary blades, and a typewriter spring mounted on a drill press. The curator's notes describe it as probably the most important kitchen gadget-turned-weapon in military history. The moral isn't about technology. It's about perspective. Sometimes a person who solves an impossible problem isn't the expert with decades of training. It's the outsider who asks a question no one else thought to ask. Whipple's question was simple. Why are we cutting individual strips? That question saved 8,000 lives. Japanese radar operators never solved the puzzle. How did one astronomer with no radar training, working in a basement with modified fabric cutter, blind the most sophisticated early warning network in the Pacific? The answer is equally simple. He didn't think about radar. He thought about geometry, mass production, and the circumference of cylinders. He applied telescope building precision to assembly line manufacturing. He brought an astronomer's thinking to a military problem and changed warfare forever. Today, every pilot who deploys chaff to evade a surface-to-air missile owes their survival to Fred Whipple. Every stealth bomber that jams enemy radar uses his principles. The technology is ubiquitous, invisible, fundamental, just like the man who invented it wanted it to be. In 1987, a reporter finally convinces Whipple to discuss his war work. The interview is brief. The reporter asks if he's proud of saving so many lives. Whipple's response, I'm proud that I was useful. An astronomer doesn't expect to be useful during wartime, but it turns out that if you study the universe long enough, you learn how to think about problems that seem impossible. That skill transferred. I'm grateful I could help. Because of Fred Whipple, 8,000 men came home from the war. Because of those 8,000 men, there are now over 40,000 descendants, children, grandchildren, great-grandchildren, who exist because one astronomer refused to accept that a problem was operationally impractical. His legacy isn't in museums. It's in living rooms, at dinner tables, in families that wouldn't exist if their grandfather's B-29 had been shot down over Tokyo on a frozen night in 1945. That's the real measure of genius, not the awards or recognition, but the quiet mathematics of survival. One man, one idea, 8,000 lives. And the humble hero who never wanted credit for any of it.